Right, in this example, we're given a first order differential equation where the forcing function has these Dirac delta functions. So you can think about these as more or less a unit impulse. And so the way you might think about this is when the time starts, we say x of 0 is at 0. Okay, so there's the initial position is the origin, say, and you immediately apply this unit impulse at that moment. And then you subtract it off a second later. And so we'll see what this will look like and see if that makes sense for our intuition. So I'm going to take the transform of each side. And we have this special property that the delta function, if it's just at the normal position, it just gives you the constant 1. But when you have it shifted, so delta of t minus 1, this will give you e to the minus s. So this is 0. So our capital X there, is 1 over s minus e to the negative s over s. So 1 divided by s, though, that's a pretty straightforward inverse Laplace transform. So this is the inverse Laplace of capital X. It would be 1, and then e to the negative s divided by s corresponds to a step function. So we're subtracting off a step function here, which is t minus 1. Oops. So what is this? If you think of this as a position function, what's sort of strange, I can see this being strange, is this delta is more or less a limiting case, right? And so you might think, well, it's kind of saying we're at 0, right, at that moment, but at that same moment, I'm suddenly going to apply this function that makes you have a unit sort of acceleration. So we're at this position, suddenly we're at 1. Just put it that way. So your velocity changed suddenly, right? So we're up there for a moment, just for a moment. And then you're sort of at resting there at that height, and then you subtract it off. And so my step at time 1, we're back down here. So that's more or less saying you to get from 0 to 1. It's more of like an instantaneous jump up that way, right? And then after that, there's no more nothing acting, and then you go down. So there you go. If you want to gather maybe a slightly more intuition about this problem, you might think how the initial problem gave you this graph of sort of the velocity, right? You could think, well, at time 0, you suddenly have this, it's kind of this infinite velocity for just a second, and then it's 0 again, because that's your Dirac delta function. And then you have, at time 1, you also have another infinite velocity sort of in the downward direction. Now, this infinite velocity, if you were to take the integral, right, it'd be equal to 1. So this is a very special type of Dirac delta function. So it's a limiting thing. And so for that moment, you have this infinite velocity, but then you had 0 velocity between. So that's why your position is steady for that time in between, and then you suddenly have a translation down. So this was could be used more or less to make like a square graph or whatnot. What would physically actually be happening, right? We're approximating here is maybe you very quickly get up to 1, and then very quickly get down. But sometimes in math, this sort of very quick move could be annoying and complicated, and so we just say, well, why don't we just pretend it was instantaneous? Make it easy on us. So hopefully that helps sort of get a little intuition there with what these delta functions are doing. And notice that you have to interpret it a little bit differently depending on if it's first order or second order in its physical conceptions. And what can be confusing, be careful about this, is in this first order problem, these deltas really correspond to sort of this instantaneous motion, so it's this type of infinite velocity. And so even though it's corresponding to a velocity, we still consider this a forcing function. At least in the vocabulary, you might see it called that on the non-homogeneous side, although that's most strictly applied in that second order case.